Let's have a quick look at the PowerPoints for Chapter 13 for analysis of variance. To tell us what's coming up in the chapters. And let's see, just signposting it for us. Experiment. What is an experiment? An experiment is something that you have control over. So if I want to check fertilizer, which fertilizer is best for my crops, I get to choose which fertilizers I use. I get to choose what crops I use them on. I have a lot of control over what happens. That's what an experiment is. So, two key features of an experiment. So again, it's you actively, deliberately manipulate the factors, and you assign the subjects randomly. So if I was going to have different fertilizers on 18 acres of land, 3 different fertilizers, 18 acres of land, like the example we saw before, I would randomly assign the different acres that get each fertilizer. And this is an example about Acela, a fast train, I guess, high-speed train. Acela is typically used by business professionals because of its fast travel times, high fares, that's interesting, business class seats, and free Wi-Fi. And basically, they want to boost young ridership. That's what they want to do. So what they're going to do to achieve that? They're going to take 16,000 college students, and they're going to give a quarter of them a 10% off coupon. So 10% off coupon for a quarter of them. See if I can highlight that. So 10% off coupon. Another quarter of them, they're going to give them a 5,000 bonus miles. And another 25% of them, they're going to give them a free Netflix movie. And the last set of people, they're going to give them nothing. So I guess that's like a control group where they're going to say, well, we gave one group a coupon, one group a bonus miles, another group a movie, and another group nothing. And if all the groups have the same ridership, then it means those offers actually didn't have any positive effect. So in this particular case, this is an example of an experiment, because what they're experimenting, they're choosing, they have some control, they're choosing what they're offering the different people on the students that are actually going to be traveling on that train. And so here's an example of an experiment. And the factor that can bring about change is the type of offer. So whether they're offering me the coupon to get 10% off, or they're giving me bonus miles, or they're offering me a Netflix movie, or no offer at all, that's the thing that can bring about change, and that's the factor. And there are 4 different levels. So the offer, the type of offer, is the factor, and there are 4 different levels, which is 10% off, 5,000 bonus miles, a free Netflix movie, or no offer at all. They're the 4 different levels. The experimental units is what we're experimenting on, and we're experimenting on the 16,000 students. They are our experimental units. And what response are we actually going to record? The response we're going to record are the miles traveled. That's what we want to look at. So what I just said is all mentioned here. So the factor is that the type of offer. There are 4 different levels: coupon, 10% off coupon, bonus miles card, a free movie, or no offer at all. And 16, the experimental units, we're experimenting on the 16,000 students, and the response variable is the miles traveled. And that's we always have to distribute the offers randomly to make sure that we don't, say, for example, give all the offers, all the, say, Netflix movies to males and all the 10% off coupons to females, because that could influence the experiment. That's why we want it to be random. how do you measure whether or not the campaign was effective? We'll use analysis of variance, and we're going to say we're going to record the average. We're going to say that mu1 is the mean miles traveled by the students in the coupon group, and mu2, mu3, and mu4, you can see what they mean. And we want to see if the averages at the population level are going to be the same. We won't have population data, we're going to have sample data, but this is what we want to find, if these averages are going to be the same. So if the average miles traveled by the people that were offered 10% off is the same as the average miles of those that were given 5,000 bonus miles, is the same as those that got to watch a Netflix movie, is the same as those that got nothing. And the alternative is at least one of those is different. Can we use ANOVA for observational studies? What is an observational study? An observational study is when you sit back and watch. So if I wanted to find out how many cars, convertible cars, are driving past on any given day past my home, I can just sit outside and actually watch them. I'm not actually influencing anything, I'm just observing what's actually happening. And you can use observational studies if you want to, but when you have no control over the experiment, you're limited to what you can observe. When you can actually influence the experiment, so going back to the fertilizer example, I can choose what fertilizers I use on what crops, when I use them. I get to choose all of that. And so it's all about controlling an experiment. They've got an example about an observational study here. And their example is about they want to figure out if people that with pets spend more in general. So if people have a pet, do they spend more money in general? So what you're going to do is observe people with pets, and you're going to observe if they spend more money in general. You're not actually going to make it an experimental study. An experimental study would be silly in this case, but an experimental study, I actually give somebody a pet and see if it changes their spending habits. So here it's asking which provides more effective way to show cause and effect. Well, the experimental study, because I get to choose what I experiment on rather than just sitting back and observing. So let's see what it says here. So this is just general information again that we've covered it, but I'm just covering it formally here in your PowerPoints. So when we're using analysis of variance, we're checking to see if the means of more than two populations are the same. If it's just we're checking to see if mu1 is equal to mu2, then we're going to use the two sample hypotheses testing. But when we want to check to see if three or more means are the same, that's when ANOVA kicks in. The alternative hypothesis is that the means are not all the same. Not all population means are the same. So here's saying if we reject the null hypothesis, we cannot, so if we reject the null hypothesis and we go with the alternative, we should not conclude that all population means are different. So it's the example I told you about in one of the earlier videos that suppose this is mu1 and this is mu2 and this is mu3. So if we reject the null hypothesis saying they're not all the same, it may mean that this is 10, this is 11, and this is 12, in which case they are all different, but it may also mean that this is 10, this is also 10, and this is 12. So again, these are not all equal. These two may be equal, but they're not all equal. So that's the differentiation it's trying to draw here. We spoke about that before. The assumptions that Fisher came up with, each population must be normally distributed. And the other one was that the variance, sigma squared, is the same for all your population data, and the observations must be independent. These are the three factors that Fisher came up with when he was developing his theory. Fisher actually looked at working out the variance, between the means, and then within, between the means and then the variation within each group, and then the comparing the variances. So he took the ratio of this guy to this guy, and we also looked at ANOVA tables. Let's see what they're saying. So these are the formulas I actually showed you before. This is working out the variation between the means. Oops. This is the variation between the means. Maybe that's not a good color to use. And that's the formula that you would use to find that. And then it's talking about the mean square of treatment. So it's actually working out the average straight away. Remember, we spoke about the variance. This is the variance, but the variability is the overall spread. And then we have to divide the variability by some number, the degrees of freedom, to get the average variability. The average variability is the variance. So they've done everything in one step. When I showed it to you, I did the top bit in one step and the bottom bit in the second step. So this is the within treatments estimate of the variance. Okay, it's the formulas we've seen before. Again, I split this out. I did it as the numerator, the total, the variation within the treatment groups, and then we worked out the mean variation by dividing out by this. Okay, and this is telling you that when we took the ratio of the mean square of treatment to the mean square of error, and basically if the null hypothesis is correct, this ratio should come to approximately equal to 1, and if it's not correct, it's going to give us a larger value. And we're going to get a chart. Always we're going to get this chart when we're dealing with ANOVA. It's always going to be a one-tailed test with rejection to the right. The do not reject is over here, the reject is over here. The reject is right there, the do not reject is over here. And if we use the critical value approach, we have to find the critical value. The test statistic is just going to be this ratio in here, and we see where it falls. So we figure out if we're going to reject or not reject. This is the table we actually come up with. So the table we actually went through in the previous example, and you have to know how to move around this table. So you take the sum of the squares of treatment, and then you find the degrees of freedom for the treatments, which is a number of treatments minus 1, and then you take this number and divide it by, you divide these two out. This is what they've done here. They've divided them out to get the mean square of treatment. And likewise, for the error term, you work out the sum of the squares, you work out the degrees of freedom, which are going to be the total number of observations minus your number of treatments. And then you're going to divide these two out, and they do that here, they divide them out, and that gives you the mean square of error. And to get the test statistic, you have to just divide these two out, and that's what they do here. They divide them out to get the f-test statistic. It doesn't show you how to get the p-value, and it doesn't actually show you how to get the critical value. So you can use f dot dist dot right to get the p-value, and we can use f dot in dot right to get the critical value. This is just saying that if we were to take the figures from down here, we can actually work out the variance using all the data, and it's talking about, this is what it's talking about here. We can just work out the variance another way, and that takes all the data into account. And when it talks about splitting the data off in these two sets, partitioning, it's just talking about analyzing this stuff. I mean, it's important, but it's not going to help you solve the problems. So the partitioning is just a way of analyzing. It's talking about that we're analyzing the different variances. So what's interesting about analysis of variance, we actually analyze a ratio of variances to actually get a result to see if the means are the same. So even though we're checking to see if mu1 equals mu2 equals mu3 and so on, we're actually checking the variances. So this is what we're checking, and we can have like this is how many treatments we've got. We got K different treatments. The one we actually looked at earlier about the fertilizer, we had 3 different fertilizers, so it would just be that. So the number of treatments would be 3, but you can have more than that. And this is how you work out the test statistic from this ratio. And then when we're using the p-value approach, remember I actually said if alpha is greater than or equal to the p-value, that implies that you should reject H0, and that's what that is saying, but they've written it, they're still saying alpha is greater than or equal to the p-value. And for the critical value approach, the second approach is that if your test statistic is greater than your critical value, it leads to a conclusion. So I'll draw it in right now. If the critical value approach, if your test statistic, which we saw on the previous page, which is the ratio of the F-test statistic, if it's actually greater than your critical value, the critical value is here, your test statistic falls over here, you reject H0, and if it falls over here, you do not reject H0. So here's an example, and I'll do that on the next video.